Okay, so today we're going to be going over Cauchy-Euler equations, okay? So, what do Cauchy-Euler equations look like? This is going to be a sub n, x to the power of n, the nth derivative of y with respect to n, plus a sub n minus 1, x to the n minus 1, and that would be the n minus 1 derivative of y with respect to x. A sub 1x dy dx plus a naught y, which equals some possibility of a g of x. If it is a non-homogeneous Cauchy-Euler differential equation. Okay? So, when we see a problem like this, the assumption that Cauchy and Euler went by was, well, what if the solution to the homogeneous portion of this problem is some just power of x, okay? So, let's let y equal, let's say, x to the m power. Okay, so we're just going to make the assumption that the solution to the homogeneous portion of this problem is a polynomial. Okay. Okay. So let's look at, if we were looking at any one of these arbitrary ones. Okay. So x to the k. Now the derivative k times of y with respect to k. Okay, so you notice that on all of these, the nth power is going to be associated with the nth derivative. So we're going to choose an arbitrary one of these and see what it looks like. Now, if y is equaling x to the m, okay, what happens when you take the first derivative? You're going to get mx to the m minus 1. Okay, now let's say I took the second derivative. Okay, well, I already took the first derivative, so we have mx to the m minus 1. So what is the next derivative going to do? It's going to spit out an m minus 1 and drop it down to m minus 2. Okay, so that would be m times m minus 1 and then x to the m minus 2. All right? Well, then what would happen with the next derivative? Okay, well, we already have we have m minus 1. What is that going to do? It's going to spit out an m minus 2 and drop it down to m minus 3. Okay? So if we do this in the most general terms, we're going to have this thing being, okay, well, x to the k is going to be left alone. Okay? But this derivative is going to be m, then m minus 1, and then m minus 2, and then m minus 3, and then dot, 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 all the way to m minus k plus 1, now x to the m minus k. So we took k derivatives. So the first derivative, it takes it down by 1. The second derivative, it takes it down by 2. If you were talking about the kth derivative, yeah, it's going to knock it down by k terms, okay? But the terms that are getting spit out, I mean, why is it m minus k plus 1? Well, why is it minus k plus 1? Think about this. When we do the first derivative, it just spits out an m. And then we have an m minus 1 in that position. When I go to the second derivative, that's going to be m times m minus 1, and then x to the m minus 2. So the second derivative just gives you m minus 1, and then x to the m minus 2. So that's why we have a k plus 1, because it's spitting out the previous terms. Okay. In general, when it comes to this problem, though, we're going to be looking at second order derivatives. Okay. So let's say Oh, sorry. Let's look at the quality that actually comes from this. We have an x to the k right here, and then we have an x to the m minus k right here. And remember, the multiplication is commutative. So the x to the k and x to the m minus k, well, the x to the k and the x to the minus k are going to cancel each other out. So this becomes m minus 1 dot 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 m minus k plus 1, and then just x to the m. And it's important that we get to that x to the m. Okay? So let's just look at a specific example of this, and let's look at a second degree derivative. Okay. So if we were looking at this problem right here, so we have a x squared, okay? This would be the second derivative of y with respect to x plus b times x dy dx plus cy, which equals 0. Isolate this away. Okay, so now this is the problem that we are considering. All right? And so we're going to say, you know what? I think this is a polynomial, so I'm going to let x to the m. Okay, so if I'm talking about y which equals x to the m, okay, I would say, all right, this is a, now x squared, and this would be m times m minus 1, all right, and then that would be x to the m minus 2 plus bx, all right, and then the first derivative of x to the m is just going to be mx to the m minus 1. Okay? Plus c x to the m, which equals 0. Right now, what we're really looking for in this problem, see, we're making the assumption that y equals x to the m. Okay? So what are we looking for? We're looking for m. Okay, so we're going to have to find a way to find that. Now notice this, we have an x squared and x to the m minus 2. Well, that's just going to turn into an x to the m. All right? So that would be a m minus 1 x to the m plus b m x to the m plus c x to the m, which equals 0. Right? And notice that everybody has an x to the m on it. So that allows me to pull an x to the m completely out of the problem. Okay, so we have big parentheses right here. Right. So we have a m minus 1 plus b m plus c times x to the m, which equals 0. Okay. Now, we don't care about the x to the m portion of this problem. You could say we could divide by x to the m. Some people would question about, well, what if it's 0? Well, I don't care if it's 0. We're not interested in that portion of the problem. We're interested in this portion right here. Okay? So, I could rewrite this problem like this. So, that would be that would be m squared minus a times m plus b times m plus c, which equals 0. Up a little bit, okay? And we want to group our like terms together, so the a and the b with the m's, let's group them together. So we have a m squared plus b minus a times m plus c, which equals 0. And this right here is this is the auxiliary equation that is going to be associated with Cauchy-Euler problems, second order Cauchy-Euler problems, okay? All right, so just like with the auxiliary equations for our standard homogeneous differential equation with constant coefficients, we got some rules that come up with is the root repeated, is the root complex, things like that. So we do have a set of rules that's going to be associated with this. All right? So if we have distinct roots, distinct real roots, okay, m1 and m2, well then y is going to equal c1 x to the m1 plus c2 x to the m2. Okay, so that's for distinct roots. Let's say we have a repeated root. And we'll just call that guy m. Okay? So, in that case, y is going to equal c1 x to the m plus c2 x to the m times the natural log of x. Okay? And the last category that we have is what if we have a complex conjugate. Okay? So let's say alpha plus or minus I and then beta. Alright? So now the complex conjugate, y is going to equal x to the alpha. Alright? Close that off. Now this is going to be c1 cosine of beta times the natural log of x. I'm going to run out of room, so I'm just going to include it right here. And then plus c2 sine of beta natural log of x. Okay. And we'll go ahead and we'll close those brackets. Okay, so this is the general set of rules that comes up when talking about Cauchy-Euler equations. So that's basically our set of rules right there for distinct roots, repeated roots, and complex conjugate roots.